Alright, so let's look at applying Dedekind's arguments to all of the different things that we have, like the reals and the rationals and the integers. Down there we get the integers. Up top, off screen, is the infinitesimals. We'll get to that one last. Okay, so to start off with, Dedekind's argument applies exactly the same way to any Archimedean group. He obsesses, like most of his proof is talking about the Archimedean property, so clearly he thinks that's important. And the way that he frames everything, he's acting like that's the only thing that's important. So yeah, it's gonna work for any Archimedean group. So it's really weird that he didn't notice that the rationals are Archimedean, but that doesn't imply that the rationals are continuous. Right, that was one of the first things that struck me when I heard about this idea. Like, what? But the rationals are Archimedean, aren't they? Yes, they are. And they're not continuous. We know the irrationals exist. And wasn't there some drama with the Pythagoreans over this? Like, allegedly there were even murders over this because it was a religious cult. But we make fun of that today because, oh, it's a science now. Math is a... Sure. Okay, so... Dedekind's argument applies exactly the same way to any Archimedean group. That is, it fails to demonstrate continuity. Right. A fact curiously amplified by the Archimedean property. So, invoking it as important as Dedekind did is really strange, right? So over here, here's a little diagram with the reals, R. Okay, so here's U1 when it doesn't include our reference value, and I've changed our reference value to 0 so that it'll work across everything, because the 1/2 isn't an integer, so we can't use that, and 0 is just a nice choice. You could use anything, 7, I don't care, 13 trillion, doesn't matter. 0 is nice to write, it's easy, it's simple to understand, sort of. So here we go. So if U1 doesn't include 0, then your gap is here. If U1 does include 0, then your gap is here. And in that gap is 0 plus infinitesimals. Okay? And there's infinitely many of these in this gap. And also, yeah, I could have filled this out a lot more. We'll get to that when we get to the infinitesimals. The point here is that there's something exists here in this gap. There are values here. There are numbers here that we actually use when we're doing mathematics. Particularly limits, when we're taking limits, when we're doing analysis. We actually use these values. We invoke these values, and it is important that we're invoking these values and not some other values, right? But Dedekind's conclusion is that everything from here to here, we're just going to call 0. Everything in this space, we just give the same name. We just give everything from where U1 ends, when it doesn't include our reference value, to where U2 begins when it doesn't include our reference value. Everything there is just called by the name of our reference value. Ultimately, that's what Dedekind cuts do. Okay? They give everything that same name. Okay? So now with the rationals, so we'll just call this 0. Right? And this is why 0.9 repeating is the same as 1. It could be, or it could be any of an infinite number of different values that are just infinitesimally close to 1. It could even be the nearest rational value below 1. We'll just call that 1. Right? It could be anything in that range. That's what Dedekind did. That's what Dedekind's completeness of the reals is accomplishing. It's really what we're doing is we're naming this space of an infinite number of values. We're giving it all the same name. We're just giving it this name right here. Everything is named after that. That central value is what everything from here to here gets named. That's what Dedekind is doing. And that's what has been accepted. Okay, now, but we can apply this to the rationals. Just the same way. It works exactly the same way. All of the arguments, everything about it works exactly the same way. Okay? So, for the rationals Q, we really just copy the diagram, except the infinitesimals become irrationals, which don't have a standard notation, I don't think. So I'm using A, lowercase a in this case. I don't care if you don't like that. Whatever. Anyway, and the reals change from being real to being irrational, so Q. So A is real in this case. So this gap that exists here, it still exists right here. Like, we just kind of shrunk it. Our whole gap is now just bigger. That's really all that happened. It's infinitely bigger. And now we're looking at, this is some random real over here and some random rational over here. This is the nearest rational below 0. This is the nearest real below 0. This is the nearest rational below 0. This is some irrational between 0 and this rational. There's going to be infinitely many of these because irrationals are also Archimedean. So there's an infinite number of these guys in this space, right? And in this space as well. There's an infinite number of these irrational values here, and then we get a mirror image of everything, right? So now everything from here to here, we're just going to call 0 according to Dedekind. So what we've done is we've taken Dedekind's argument for the reals, and we've just applied it to the rationals, because there is no reason whatsoever why that shouldn't work. Nothing in the proof requires us to be applying this to the reals. All it actually is requiring is that we apply it to an Archimedean group. So we can apply it to an Archimedean group with known gaps. Okay, so we have the rationals, we know that the irrationals exist. So we have known gaps in this Archimedean group, but there's nothing about Dedekind's proof that requires us to operate over the reals. He specified that, but you don't need to. There's no real reason to do that. We can do it to the rationals, and the argument comes out exactly the same way, except now the range of values that we're calling by the name of our definite reference value, it just increases. It's just a larger group of things that we're all calling by that same name. Now, let's note that the inclusion of the Archimedean property doesn't actually accomplish anything for us. It's for some reason everybody seems to interpret it as the inclusion of the Archimedean property is what makes these things continuous. No, it isn't. It doesn't do that at all. It doesn't matter, because what ends up happening is we get down to a point where we can actually meaningfully talk about the closest real to our reference value on either side, because we know how to talk about the gap in between. There's something between those. So if we just look at our reference value, and like as we move away from it towards the other guys, if it's reals or rationals, whatever it is, as we move towards the next one, we're going to run into something that isn't part of that category before we run into something that is part of that category, right? So the gap exists, right? That's all that actually matters, right? So Dedekind is coming at it from the wrong direction. He's like, oh, we never reached the gap, so it doesn't exist. No, that's not true. If you go the other direction, you hit the gap first. And it's all you see. You can go through that gap forever. You can run through infinite values and still not even be any percentage of the way through it. Because it is the width of that gap in terms of how many values are in there is absolute infinity. There's that many of them. You're never going to step through those, right? And that's the nature of the infinitesimals. Anyway, so the inclusion of the Archimedean property doesn't actually do anything for us here, so we can ignore it and apply the rest of Dedekind's argument to discrete sets as well, like the integers. And we end up with exactly the same failure. It looks exactly the same, right? So with the integers, Right? We get this gap between 0 and the next, the integer below it, which we have a name for that one. It's 1, or it's -1, and the integer right above it, and we have a name for that one. It's +1. Right? Notice these aren't natural numbers; these are integers because they're signed. Okay. Anyway, so between those, we have an infinite number of rationals, or an infinite number of reals, or an infinite number of infinitesimals. It doesn't matter which of those groups we choose. They all exist, or an infinite number of irrationals, or an infinite number of transcendentals. Like, we can take frickin' anything. Any one of those Archimedean groups, drop it in there. Frickin' the infinitesimals aren't even Archimedean. It doesn't matter. Any of these groups that lives in that space, we can drop them in there and be like, hey, look, there's a gap here. And it still works exactly the same under Dedekind's argument. What we're going to do is we're going to ignore the gap. And we're just going to name everything based on our reference value 0. So the conclusion is all integers are equal to 0. This is what Dedekind's proof actually says. If we properly analyze everything, if we step through everything and look through all of the parts of it, this is one of the things that it says, that all of the integers are exactly the same as 0. Or all of the integers are exactly the same as 73. Or all of the integers are exactly the same as -416 cubed. You can pick any integer, and under Dedekind's argument, they all have that name. This is the problem. Or this is, yeah. I don't know if this is the problem. This is a pretty big problem, though. This is a problem that comes out of this that nobody apparently cares about. So, bravo. Good job. That's just... wow. Fantastic. Now let's actually look at the infinitesimals up here, right? So here's the infinitesimals. So these guys are properly continuous, okay? So we have our reference value 0 here. I'm using 0 to be consistent. Over here we have a real value. Let's say it's the nearest real to 0 in this direction, right? And this is the nearest real to 0 in this direction. Okay, so there's infinitesimals that are all, this one is the nearest neighbor to 0, and then its nearest neighbor, and its nearest neighbor, and there's an infinite number of these. So n is natural numbers, right? So the infinitesimal unit, that's what that is right there, right? We're the infinitesimal unit away from 1, and we can go any number of those away, and there's still going to be a gap in here, and we've got the infinitesimal units away from, here's our real infinitesimal units away from this real, right? And this space here, this is continuous. This is properly continuous. Each value has a neighbor. Each value has a definite neighbor that we can actually talk about now that we've recognized that infinitesimals exist. That they occur in this gap here between the reals. So what this infinitesimal unit right here is, it is the inverse of absolute infinity. That's what it is. 0 is not the inverse of absolute infinity. 1 over 0 is not infinity. 1 over this guy is. Okay? And there's infinitely many of these coming away from 0. There's infinitely many of these coming away from this real on both sides. I just didn't fill in these, but they're over here, and it just extends forever, and this extends forever, and you still have a gap between them that we don't have any way of talking about. We don't have a notation that handles this, and you can't. The transfinites isn't going to work, right? A left notation, whatever the hell, it isn't going to work here because already that's being used up here. Because this extends, there's an absolute infinity of these. Absolute infinity is larger than any value you can find with a left notation, because those are all transfinites. They're smaller than absolute infinity. There's more of these than you can talk about with that notation. You can never get here using any notation that exists. You can never talk about this space. There is no notation for handling this currently. Right? Are we seeing the problem here? What acceptance of Dedekind has done is we just refuse to acknowledge how this shit actually works. Now, Now, I've been meaning to say this for a while, but there is virtue in calling these the reals. There is a virtue in this because any actually physically measurable value is included here. That's useful. So any physically realizable measurement is a real value. It's not going to be an integer. It's not going to be a natural number. It's going to be a real value. Right? Because you can have, well, this isn't a whole apple. It's 99% of an apple. So it's 0.99 of an apple. That's a real value, not an integer. Right? These are, this is a good name in a sense. Imaginary, for those, not such a great name, but I don't know. I can't think of a better name actually than this. You just need to like think of it slightly differently. Like the real numbers are realizable numbers. Not all of them actually. So like down at this level, there's absolutely no way you're ever physically finding the difference between this and 0. In that sense, what Dedekind is doing here, where we're establishing that we'll just call this 0, and we'll just call this 0, and we'll call this 0, and we'll call this 0, it has practical merit. It does. It does have practical merit. But using it as an axiom of your foundation of mathematics is not smart. Because its implications are dumb. Its implications are just no. No. So there's merit to this, but it's mostly in terms of physically realizable measurements. If what you're trying to do is pure mathematics, you need to get beyond Dedekind cuts, because Dedekind cuts don't actually work in that way. And even for really properly understanding some measurements and things, like it's not ideal to go down this path.